The next speaker is Dr. Ryo Shintani. The title of his talk is Catalytic Asymmetric Synthesis of Silicon-Stereogenic Organosilanes. Please.
Thank you for the introduction. I would like to follow the previous speakers to thank the Yamamoto sensei and Suzuki sensei, as well as other committee members and Banyu Life Science Foundation. And I completely changed the title from the MBLA application in 2011. I would like to share with you our recent work on catalytic asymmetric synthesis of silicon-stereogenic organosilanes. This is a summary slide for the application of 2011 MBLA. And at that time, I was mostly working on the development of catalytic asymmetric or selective synthesis of cyclic compounds, particularly using this cyclic lactones as the versatile reagent for the 1,4-Zwitty ionic species under palladium catalysis, and we could synthesize a variety of different carbon heterocycles shown here. And we could also control the carbon stereogenic centers, such as this, enantioselectively in many of these cases. And as all of you know, many carbon stereogenic centers are widely available, and still there are lots of research activities are going on in the field of organic synthesis. But if you look at silicon instead of carbon, although organosilanes also constitute functional molecules in the field of material science or pharmaceutical science, there are not many efforts or examples of synthesizing silicon-stereogenic organosilanes enantioselectively. And recently, we switched our research field directed toward the synthesis of silicon-stereogenic organosilanes under transition metal catalysis in an enantioselective manner, particularly focusing on the use of this type of prochiral organosilanes as the starting compound. And through desymmetrization, one of these silicon-carbon or silicon heteroatom bond, we could probably synthesize a variety of different organosilanes having silicon-stereogenic centers. And our goals are to develop syntheses as well as investigate the properties as well as find utilities of these organosilanes. And due to the time limitations, today I focus on the synthetic portion of our recent efforts. And if you look at the literature for the transition metal catalyzed asymmetric synthesis of silicon-stereogenic organosilanes, they almost always utilize dihydrosilanes of this type as the prochiral substrate. And effective desymmetrization of silicon hydrogen bonds selectively one over the other, they could synthesize the silicon-stereogenic compounds. For example, in 1994, Professor Takaya reported the ketone hydrosylation using this type of prochiral dihydrosilanes using rhodium cyclohexyl binary system, giving the corresponding silyl ether in greater than 99% EE. And another example shown here was developed by Professor Katsuki, and they described the use of iridium silane complex as an effective catalyst for the insertion of diazo compounds to silicon hydrogen bond to give the corresponding silicon and carbon stereogenic compound with high diastero and enantioselectivity. Now, what we thought about utilizing as prochiral substrate is actually the tetraorganosilanes of this type shown here. And the first type of compound came into our mind is the silocyclobutane shown here. And selective cleavage of carbon-silicon bond shown here would provide the silicon-stereogenic compounds in an enantioselective fashion. In 1975, Sakurai and Imai reported palladium-catalyzed formal insertion of internal alkynes to silocyclobutanes takes place to give the corresponding achiral silocyclohexene in high yield. Based on their chemistry, we devised the intra- and intermolecular variant having a prochiral silocyclobutane shown here. We initiated a program having an alkyne attached intramolecular version of the Sakurai-Imai reaction, and we found that the use of newly synthesized chiral phosphoramidite shown here was particularly effective in inducing high yield and enantioselectivity for this intramolecular transformation, giving the silicon-stereogenic polycyclic compound shown here in high yield and enantioselectivity. And later on, we also found that the same catalyst system having this phosphoramidite ligand was also effective for the intermolecular reaction between silocyclobutane and electron-deficient alkynes to give the corresponding silocyclohexene with the same level of enantiomer selectivity. And this type of compound can be further elaborated by utilizing the silicon-stereogenic centers we created in the previous reaction. And for example, the hydroboration of this compound takes place selectively at this olefin in Ryo selectively and distereoselectively to give this alkyl boronic acid exclusively after acetic acid workup. We can also hydrogenate this same molecule in the same sense of distereoselectivity to give the saturated silocyclohexane, and this aryl group can be effectively cleaved in treatment with the triflic acid followed by LAH reduction to give the corresponding monohydrosilane with retention of configuration at this silicon-stereogenic center. For the monocyclic silocyclohexene, we could also hydrogenate this olefin distereoselectively to give this silocyclohexane having 3 contiguous stereogenic centers exclusively with retaining the enantiomer selectivity. Selective reduction of this remote ester group by treating it with diol H provided the bicyclic lactone shown here, or we could fully reduce both of these esters to diols by treating it with the excess amount of lithium aluminum hydride. And based on our initial success using silocyclobutanes as the prochiral substrates, we moved on to different class of silicon-stereogenic compounds more relevant to the material science. And the target of our compound is shown here, dibenzylol shown here. Because of the utility of dibenzylol framework in the material science, there are lots of researches going on in terms of efficient synthesis of dibenzylols under transition metal catalysis. For example, Professors Shimizu and Hiyama reported in 2008 that by using palladium acetate and tricyclohexylphosphine as the catalyst, they could do intramolecular CH arylation of the silicon-attached aryl triflate to give the achiral dibenzylol of this type in high yield. And we designed the prochiral version of this chemistry by having 2 of the same phenyl group on the silicon atom. And by differentiating 2 of these phenyl groups in the event of CH arylation, we thought we could synthesize the silicon-stereogenic dibenzylol shown here. And at the beginning, we examined the effect of ligand, and we borrowed their initial conditions, namely palladium acetate and tricyclohexylphosphine, to examine the reactivity of this particular substrate. And we found that the generation of the desired compound was observed in 44% yield in a racemic form. But in addition, we also observed the formation of achiral dibenzylol of this type, having a CC bond formation between these 2 phenyl groups in 37% yield. We subsequently found that the use of electron-rich bisphosphine ligand was particularly effective for suppressing this undesired formation of achiral dibenzylol, and Josifos was effective for inducing high enantiomer selectivity of 82% in DMA at 60 degrees. And by changing the solvent from DMA to toluene, further improvement of yield and EE was observed. And modification of diphenylphosphino group of this Josifos to substituted diaryl phosphino group, optimal result was obtained with up to 94% EE. And under these conditions, we could synthesize a variety of different dibenzyls having different substituents, as shown here. We could install different substituents at different positions of the dibenzylol, or we can incorporate the bicyclic compounds such as naphthyl and indole moiety with high enantiomer selectivities. Or we can dismetrize having 2 of the same substituted aryl groups instead of simple phenyl groups to have more conjugated dibenzylols with high enantiomer selectivity as well. And in addition to this intramolecular synthesis of dibenzylol, we recently devised a method of intermolecular synthesis of silicon-stereogenic dibenzylol through 2+2+2 cycloaddition chemistry. And if you look at the literature in 2007, Professor Murakami reported an iridium triphenylphosphine catalyst system for the intermolecular 2+2+2 cycloaddition of these 2 components at 110 degrees to give the corresponding achiral dibenzylol in high yield. In contrast, in our system, we utilized the prochiral triene as the reaction substrate, and we found that the rhodium cationic complex was much more reactive in this catalysis. So when we use rhodium as the central metal in combination with our binap as the chiral ligand, we could observe the 74% yield of the desired silicon-stereogenic product. But the enantioselectivity in this case was only 18%. And as a control experiment, just by switching rhodium to iridium in this case, we observed no formation of the desired compound at 25 degrees, indicating that cationic rhodium catalyst is much more active in this particular case. And after screening several chiral ligands, we arrived that this monodentate chiral phosphine ligand shown here was suitable ligand for inducing high enantioselectivity in this transformation, and ranging from 85% EE to 92% EE for the formation of silicon-stereogenic dibenzyl. We can change the alkyl substituents here or aromatic groups here, or we can even change the tether from benzene to thiophene to have a heteroatom containing dibenzyl derivative in high EE as well. And when we use the unsymmetrically substituted internal alkyne as the reaction partner, we can regioselectively couple these two components to get the dibenzyl in high EE as well. And the last topic of today's presentation is the synthesis of dibenzoxacylane shown here through the strategy of enantioselective transmetallation. So this idea is summarized in this slide by having hydroxy-attached biphenylsilane as the prochiral substrate in the presence of catalytic amount of chiral rhodium hydroxide. This generates this type of intermediate shown in the middle. And through this intermediate, the intramolecular delivery of the aryl group transmetallation from silicon to rhodium would take place to give the resulting silicon-stereogenic dibenzoxacylane product. And in this reaction, we found that methyl diphos was particularly effective for inducing high enantioselectivity, and under the conditions shown here, this substrate undergoes intramolecular delivery of phenyl group from silicon to rhodium through this type of intermediate to give the corresponding product with high enantioselectivity. But during the course of our study, we found that the ratio of rhodium and diphos was particularly important to reproducibly provide the desired compound with high stereoselectivity. And when we used no ligand, no diphos, just rhodium, gave no reaction. But when we used slight excess of rhodium, 8 mol% of rhodium, 6 mol% of ligand, we got high yield and high EE, as I showed you in the previous slide. But if we increased too much amount to 10 mol% of ligand to 8 mol% of rhodium, we got high yield of the product, but racemic product was generated. And based on these results, as well as our mechanistic studies using rhodium diphos complexes, our current hypothesis is as follows. As I showed you here in red, rhodium olefin complex shown here is an inactive species, so this does not generate any of this compound. But when we have one diphos on rhodium in a chelated fashion, this orange rhodium complex shows high activity and enantioselectivity to give this silicon-stereogenic compound with high enantioselectivity. But if we have too much diphos, 2 diphos on 1 rhodium, this blue rhodium complex shows much more active catalytic activity, but non-selectively provides the racemic product. Under the desired conditions, we could synthesize several dibenzoxacylane shown here, having different substituents here or here at both biphenyl backbone. Or we can differentiate 2 of the same aryl groups instead of simple phenyl group to have this type of substitute phenyl groups on silicon atom. The product thus obtained can be ring opened in the presence of alkyl lithium to generate this type of tetraorganosilanes with retaining the silicon-stereogenic configuration, although 91% EE of the substrate becomes 88% EE. And in summary, we have been developing the effective method of synthesizing silicon-stereogenic compounds through the dismeterization of prochiral organosilanes under transition metal catalysis. And we are also now trying to investigate the properties and utilities of these newly synthesized organosilanes. And finally, I would like to thank these co-workers, particularly Professor Tamio Hayashi and Professor Kyoko Nozaki, and several other faculty members. And also, I would like to thank these current and previous co-workers who did actual experiments. And I would like to thank the funding agencies, and thank you for your kind attention.
Thank you for a nice talk about formation of silicon